calculate G. For C, that would be 8. For E, that would be 6 plus 2, 8 again. But about S, because S is already in my visitor list, I don't calculate the value of G for S and consider it a dead end, because if I want to expand this node, I will stuck in a loop. Here would be C star. And we say epsilon is the minimum cost between two adjacent nodes. So we can call it this is epsilon, and this is epsilon. So to find out the number of nodes that we checked in this path, we have to divide C star on epsilon to find out the number of nodes. Hello everybody, welcome back to another video in Artificial Intelligence course in Farzin Academy YouTube channel. Well, so far we've discussed about two uninformed search algorithms, BFS or breadth first search and DFS or depth first search. And if you like to watch the other videos, I provide the link of this playlist in the description of this video. So all you have to do is to click on the link and all videos of our AI course will be shown and you can watch whatever you want. But about this video, we will discuss about uniform cost search algorithm, or in abbreviation UCS, one of the most important search algorithms in this course. And the interesting thing about this algorithm is this is an optimal search algorithm, and we'll discuss about that. So let's start our video. First of all, it's very good and suitable for when the cost differs by step count, or it means in our graph, edge weights vary, just like the example that we have in the other two videos, and we'll discuss about that in this video. And the expansion priority is given to the node with the shortest path. So to reach this purpose, we will represent a function gn that tell us what node is appropriate for expansion. This function works like this, that it has an input n that would be a node, and gn will return the value of all costs from initial state to reach node n. So let me tell this by an example. Consider I have my search tree like this. I have S, then with 2 and 3 I go to A and B, and from A with 5 I go to C, and with 1 and 4 I go to D and E. So when I say G, for example, E, it means starting from the initial state to reach node E, how much cost I have to pay. So node E is here. To reach from our initial state node S to node E, I have a 2 and 4. So GE would be 6, the addition of these two values. Or for example, for node D, this function will return, node D. This function would return 2 plus 1, that would be equal to 3. So this is how we calculate G of each node in this algorithm. And UCS chooses the node with the least value of Gn. So if you just take a look to this figure, we have a initial state node S and two nodes n' and n. And for reaching n', we have gn', and to reach n, we have gn. So we have to choose the node with the least value of g. So if gn is less than gn', that means we have to expand the node n, because the g of n is less than n'. So this is the whole thing about UCS, and right now we have run uniform cost search algorithm on the following graph. This is the graph that we will discuss about for all search algorithms that we have in this course. So on the left side, like always, I have my graph, and on the right side, I want to create my search tree and find out the path to reach one of the goal nodes. And just like always, I want to use a visited list or a closed list to prevent duplication in my search tree. So let's start it by expansion of my initial state. That would be node S. So node S has 3 children according to the graph on the left side, node A, B, and D. So I have A, B, D as children of node S. So I can say S is expanded and I can add it to my visited list. After that, I have to calculate the value of G for each node. So because we have just one edge between these nodes and initial state, the value of G will be equal to the cost of each edge. For example, for A, that would be 5, for B, that would be 9, and for D, that would be 6. So from these 3 values, I have to choose the least one. So that would be node A with value of 5. So I have to expand node A. According to the left side, node A has 2 children, node B and G1. So I expand node A and I mark it and add it to my visited list. And it has 2 children, B and G1. To calculate the value of G for each node, I have to calculate the sum of all edges costs in the path. For example, for B, that would be 5 plus 3, that would be 8. And for G1 is 5 plus 9, that is 14. So I have to check nodes that are not in my visited list to choose expansion. So I have one B, one G1, another B, and D. So I have to choose the node with the least value of G. I have 8, 14, 9, and 6. So the least one is node D with value of 6. So I expand node D. According to the left side, node D has 3 children, C, E, and S. So I have to calculate the value of G. 6 plus 2 is 8. Before that, let's mark D and add it to my visited list, then calculate G. For C, that would be 8. For E, that would be 6 plus 2, 8 again. But about S, because S is already in my visited list, I don't calculate the value of G for S and consider it a dead end, because if I want to expand this node, I will stuck in a loop and it's not an efficient path. So I have these nodes B with value of 8, G1 with value of 14, B with value of 9, C with value of 8, and E with value of 8 again. So I have to choose the node with the least value of G. The least value would be 8, and there are 3 nodes with value of 8. So I have to pick one randomly. So consider I just pick node B. B has 2 children according to the left side. B has one child A and another child node C. So A and C are here, but let's mark node B and add it to my visited list. And A is already in my visited list, so I prune it and I won't expand it. And node C, if I want to calculate the G of C here, that would be 5 plus 3 is 8, and 8 plus A is 9. So I have 9, 14, 9, 8, and 8. So to choose the least one, I should pick randomly between C and E. So consider I pick C. C has 2 children again, G2 and F, and also S. That I don't provide S here because it's already in my visited list, and I just want to prevent this search being so crowded. By the true thing is to have S here too. But anyway, so I have G2 and F. If first of all, let's mark C and add it to my visited list, and then calculate the value of G for each node, G2 and F. For G2, that would be 6 plus 2, 8, 8 plus 5 is 13, and 6 plus 2, 8, 8 plus 5 is 15 for node F. So I have node C with value of 9, G1 with value of 14, B with value of 9, G2 with value of 13, F with value of 15, and E with value of 8. So I have to choose the least one. So I expand node E. E has just one child, G3, with value of 7. So node E is marked and added to my visited list. And also I calculate the G value of G3, that would be 15. So far in node E, that would be 8. 8 plus 7 is 15. So here I have C with 9, G1 with 14, B with 9, G2 with 13, F with 15, and G3 with 15. So the least one would be node B, but B is already in my visited list, so I won't expand it. The next one is node C, but node C is again already in my visited list, so I won't expand it. And the list value, I have to pick it between G1 with 14, G2 with 13, F with 15, and G3 with 15. So the least one is G2 with value of 13. And this is my goal node. And the path to find this goal node is S to D, D to C, and C to G2. And interesting thing is this solution is optimal, and you cannot find a better path than this path. You can reach one of the goal nodes with value of 6 plus 2, 8, 8 plus 5, 13. This is a very good search algorithm, and as you can see, it helps us to find an efficient and optimal solution. So let's see properties of UCS. First of all, completeness. We can say UCS is complete because the algorithm searches the entire state space in the worst case and will find a goal if it exists. So I think it's clear that it's complete because in the worst case, we'll check all nodes in our graph. Next thing is about optimality. And as we can see in the previous example, we can say it's optimal and finds the shortest and best path. About time and space complexity, we have this is statement. We can say it's big O of B with power C star divided to epsilon plus 1, and C star divided to epsilon is in a floor. So let's discuss about this formula, and we'll see how we come up with that. As I wrote here, C star is a cost of optimal path. So let's have a simple figure. Consider we have this path to reach my goal state, and the total cost path of here would be C star. And we say epsilon is the minimum cost between two adjacent nodes. So we can call it this is epsilon, and this is epsilon. So to find out the number of nodes that we checked in this path, we have to divide C star on epsilon to find out the number of nodes. But this number would be not an integer. So I use a floor operation to make it integer. And because we are dealing with big O, I have to choose the upper bound. So I add a simple 1 here. And because we're dealing with branching factor B, this would be the power of B. So this is how I come up with this following formula for my time and space complexity. So this is the end of this video. If you enjoyed this video, it would be a great help for me and my channel to subscribe my channel, like this video, and share it with your friends who are interested in AI and computer science. Thank you very much. See you later.